back, everybody. So last class we finished up what was really the math review, and we had talked about before. We introduced our coordinate system. We talked about vector calculus, different types of multivariable calculus, partial derivatives, and vector structures and things. And then we talked about last class. Taylor's theorem was in there. We focused on Taylor's theorem quite a bit in one dimension and then in multiple spatial and time dimensions. And then last class, we really just talked mostly about two main topics, mostly differential equations, and then also a little bit of dimensional analysis that we sort of fit in right at the end. So just as a reminder, so differential equations are really, really central in physics because most of the physical laws, like say Newton's second law or the laws of fluid mechanics, like the Navier-Stokes equation that we're going to be getting to, they are formulated in terms of differential equations, which might not be obvious from looking at an equation like F equals ma, which we just normally think of just as a force law or something. But really, this is a differential equation because the acceleration is the second time derivative of the position. And so F equals ma is really a second order differential equation with two time derivatives. And it allows us to, if we can solve that differential equation, it allows us to now predict what is the trajectory of the particle for all future times. So x of t would be the solution to the differential equation. And so usually x of t, we write it as a vector, so it's three components, x of t, y of t, z of t. And so the point is that this law of physics is really a differential equation that if we can solve it somehow, maybe using tricks from a differential equations class, or maybe numerically, as I'll get to in a second, it gives us an explicit prediction for where the particle is going to be in the future. And that's something we very often want to do. You know, you want to model like where a weather system is going to be, or if you were doing really any kind of physical modeling sports, like modeling the position of a baseball, or designing something that fires projectiles, for example. You would want to be able to predict the positions of particles. And so that's what differential equations really are for. They allow us, if we can solve them, to make predictions for the future. And F equals ma is a classic example. So these are really prediction problems, and that's why they're so important. And so we talked about basically two general categories of differential equations, linear versus nonlinear. And so a linear differential equation is one where the right-hand side of the equation, so in this case I've written here, so W is the variable we're trying to solve for, and in our example that was the fall velocity of a particle. And this particular example is just falling under gravity only, so we just have minus g as the acceleration on the right-hand side. But this would still be linear if, for example, we added a linear drag term to it. So for example, if we added a term like minus beta w, where beta is just some constant, then this would still be linear because the right-hand side, it only depends on w up to the first power. So it doesn't have, for example, w squared or w cubed or anything like that. And so it's a fact of applied math that if you ever encounter any linear differential equation, it always has an exact solution. So there's some method to come up with like a pencil and paper solution for what that function is. But when the equations are nonlinear, so for example, here we have dw dt, that's the fall velocity, the rate of change of the fall velocity is affected by gravity, and then also this quadratic drag. So this is, for example, a wind resistance on a falling particle. This equation is nonlinear because it has this w squared here. And in most cases, nonlinear problems actually don't have an analytical solution. This one turns out to be a little bit of a quirky example. There is a special trick that you can use to solve it, but in general, when you encounter a nonlinear equation, it's fairly hopeless. Like it might be solvable using certain special tricks, but most of the time it isn't. And the equations that we're going to encounter in fluid mechanics are, in general, they're nonlinear, and we're actually going to start to see where that nonlinearity comes from today. But so what do we do in that case? We still want to do the prediction problem, right? We want to know how the system is going to behave in the future. For example, if we want to do like numerical weather prediction, we want to know what the weather is going to be like in a couple days. We need to solve differential equations. We run into these nonlinear ones that are not traditionally solvable. So what do we do? And so we talked about this very general technique called Euler's method. And I've just written down sort of the final formula we arrived at here. And the idea of Euler's method is that we take the time range over which we want to solve the equation. So for example, we had t equals 0, and that goes up to, say, t equals 10. We want to solve the equation. We know the initial condition. We have the initial condition, or IC, specified at t equals 0. We know the state of the atmosphere at time equals 0. And we want to know what's going to be the state of the atmosphere at t equals 10 hours from now or something. And so what we do is we take that time window, which at the start is continuous, right? There's an infinite number of moments in between now and 10 hours from now. And we chunk it up into little small pieces, each one of those little pieces has a duration delta t, and that's called the time step. And when we do that, we can basically construct a system by approximating the differential equation, where we can use a sort of an iterative step-by-step procedure to predict what the value will be of our particular function. Let's say it's w, for example, our fall velocity, or something about the weather. We can basically start at t equals 0, where we know the initial condition. That always has to be given to us. And then we can use Euler's method to step forward the solution. Use 0 to predict 1, and then use 1 to predict 2, 2 to predict 3, and step forward like that, until we get all the way to 10, which is our final forecast that we would like to make. And this method in general is called numerical solutions of differential equations, and there are at least a few whole courses that are on this kind of idea. But in this course, we really just need to know the basic concept, which is that we sort of always have to discretize things. We break up our time from continuous into these small, discrete chunks, and then we step forward the solution iteratively. So it fits very nicely into the framework of like a for loop that you would write in Python. And so on the first assignment, you get to apply this technique just to a very simple equation that governs exponential decay of like a radioactive substance. And so we're going to return to this idea, applying it to different equations throughout the course. But so far, though, we've just sort of reviewed the general method, and we're applying it to sort of toy equations that don't necessarily come from fluid mechanics. And then the last point we made was about dimensional analysis, totally separate topic. It's not differential equations. And this is about essentially how do we track and make sure that when we have equations that are meant to come from physics, that they make physical sense. And so one thing that is just sort of, I guess it's kind of like, obvious in some way, is that you can't add a distance to a time. Like a minute plus a kilometer doesn't make any sense. Like what is that, right? So whenever you have an equation, we have different things added to one another, or an equation with quantities on both sides of an equal sign, then those things always have to have the same dimensions. And we made the distinction between dimensions and units. So a unit is like meters per second or kilometers per hour or whatever. And that's a way that is actually a standard metric by which we quantify speed. So you can say something is 10 meters per second, but you could also represent that in terms of kilometers per hour. So with units, for any given quantity, like say the speed of a ball flying across the room, you can represent it in meters per second or kilometers per hour or whatever light years per millennium or whatever you want. And there's many different ways to represent this in terms of units. But dimensionally, when we say that something's dimensions, we mean that the speed is length per time. So there are really only, the fundamental dimensions are length, time, mass, electric charge, and temperature. And we're really mostly going to be focused on length, time, and mass in fluid mechanics. Temperature and electric charge, that's a Q, are not going to show up too much. But the idea here is that velocity has dimensions of length per time, and there's a unique dimension. There's not many different ways to represent it. There's just that unique way. So you can calculate. So we denote dimensions of a quantity by these square brackets, and we did a couple of examples at the end of class. And one of them was kinetic energy. So here, capital K represents kinetic energy. So if you wanted to know what are the dimensions of kinetic energy, you can just plug in the formula here. The classical formula is 1/2 times mv squared. The dimensions of any product are equal to the product of the dimensions. The half factor is dimensionless. The dimensions of mass are capital M. The dimensions of velocity squared are L squared per time squared, so length squared per time squared. And so then this would be our final answer for the dimensions of kinetic energy. And so this turns out, so it looks awfully simple when you're dealing with just simple things like projectile motion or the energy of a single particle and things like that. But when you get into fluid mechanics, what are the dimensions of pressure? Or what are the dimensions of buoyancy or something? And it's not as obvious. And so tracking things by looking at how they are related in equations is a very useful way to, for one, make sure that you haven't made a mathematical error somehow, because if your dimensions don't work out to be the same on both sides of an equation, something must have gone wrong in your calculation. And the other reason it's very useful is it's useful to interpret the sort of physical meaning of terms in the equations, because it just tends to be true in physics that if something has dimensions of length per time, then it usually has some kind of interpretation in terms of a velocity. Like it's a velocity of a gas or something. And in individual cases, that can be very illuminating. We'll see some examples as we go through the course. Okay, so today we're going to move on from the mathematical review, and we're really going to start talking about fluids. We'll start by thinking about how we can apply principles of physics like accelerations and forces to fluids, which is not usually what we do. So when we learn first year mechanics or in high school or even higher level courses, we often think of baseballs flying through the air or a solid body sitting somewhere on an inclined plane or whatever, and you're analyzing forces on a coherent body that's moving. Whereas a fluid is different, because the particle it's made up of a continuous set of particles that are all sort of moving relative to one another. And so how to apply Newton's laws to that are a little bit less obvious, and so that's what we're going to talk about today. But I'll just pause at the beginning. Does anyone have any questions about maybe the homework or any of the review? I think the homework is due on Friday. And I think all of the material should have been covered already, but maybe the context hasn't been covered. So I think we're going to cover the last bit of context today. But anyone have any questions? Okay, great. Okay, so this next section, which is going to be a fairly long section, is called the fundamental equations. This is called section 3. Section fundamental equations of fluid dynamics. Okay. So, in the notes I motivated this a little bit by talking about numerical weather prediction, but so when we're studying something like fluids, I like to go to meteorology as a key use case, and oceanography is very similar. That something that we very much want to do is know what, say, the winds are going to be like sometime in the future. So a classic prediction problem of interest is what will be the winds, let's say the surface winds, at each location xy at some point in the future. And of course, this is very relevant these days. We're having all these windstorms. If you want to make your day-to-day plans, you want to know how windy is it going to be in my particular region in a few days when I'm planning on doing something. And if you were interested not only in just our own lives at the surface, but also maybe in aviation, like flight planning, or if you were interested in sort of the atmosphere in general, you might even want to know what's happening in 3 dimensions, in X, Y, Z. So what are the winds going to be at every place in the atmosphere, both at the surface and in the center of the atmosphere, at some future time. And so what this really relates to, so the mathematical quantity that we're asking about is the velocity field. So we have this vector field, so we always say, so it's u with a vector symbol, and that depends on our position and on time. And that's a 3 vector, which has 3 components, which we always call u, v, and w. And all 3 of those are functions of space, the x, and time. So if we knew this somehow, then we would have the answer to our question. So if we had a spreadsheet that said for all different positions x and all different future times, here's the velocity vector, here's the winds, then that would be exactly what we want. That would tell us how windy it's going to be at every location in the atmosphere at every future time. Okay. So so this object is called the velocity field. And so to predict u of x and t for future times, we need an equation. Usually it's a differential equation that we can solve. And this is going to end up being the Navier-Stokes equations. But the challenge is that it's not too ridiculous to think that maybe we could come up with an equation that we can solve to determine this velocity field, because we know that the fluid is made up of this material stuff. It's water or air or whatever, and so that fluid interacts with itself according to normal physical principles like forces and accelerations, and we know something about the forces, like there's pressure forces involved. We're going to cover those in detail later. There may be factors involving temperature or buoyancy or density, and so it's maybe reasonable to think that if we combined all these pieces of physics together, we could get some kind of predictive system for predicting what the velocity field is going to be in the future. But the challenge is that we want an equation for a field, which is a function of space and time. In our case, it's a vector function. Whereas Newton's laws apply to particles or bodies. So, we really want to know how the velocity field is going to change at a particular point in space, right? We're interested in not necessarily where all of the air molecules are going over time, but we want to know at a particular location, at a particular time, what's the wind going to be like, or what's the temperature going to be like. And so there's sort of a conceptual gap here. We know how to apply Newton's laws to particular particles, but what do we do if what we want is not the particles, but what we want is sort of the collective description of what all the particles are doing in terms of the velocity field. Okay. So it turns out the dynamics of the velocity field can be connected to the physics of individual fluid parcels. And I'm going to describe what do I mean when I say a fluid parcel. And this idea is due to Euler, who's a famous mathematician after whom lots of stuff is named. Okay, so basically, so what we're trying to do is we're trying to develop an equation that will allow us to predict something like the winds at future times. And the only tool we really have to do that is Newtonian mechanics, right? How sort of forces affect how things move. But there's this gap that we want to know a field, and we have a technique for particles. And so Euler allows us to connect these two things. And it's really done using the concept of a fluid parcel. So a fluid parcel is a small region of a fluid. And we can say it has volume dV, so it has some infinitesimal little tiny volume. And the key thing is that this fluid parcel, it moves with the flow. So we think of these parcels as being embedded in the flow. So I think a diagram is sort of helpful. So let's say this is the ground, and we have the surface of the ocean at the top. And so now inside this, so we have water up here, and then here's the ground down here. And so a fluid parcel is really just a little, we often think of it as a little cube of fluid that is part of the whole of the fluid. And it's moving in whatever direction the velocity field is going at that particular point. So this would be our parcel. And you could draw them anywhere. The whole body of fluid can be divided up into many, many of these parcels. And the technique is going to be that we're going to consider these parcels to be small enough that we can treat them just like traditional particles in Newtonian mechanics. And we won't have to worry about the sort of global structure of the fluid. We're just going to look at what's happening physically to each little tiny piece of the fluid, and then we're going to be able to put all those pieces together and come up with an equation that will allow us to predict the velocity field in the future. Okay, so a really key thing to remember is that all of these parcels, they're embedded in the flow. So if they're all, and they all may be moving slightly different directions, but for example, in this case, if the flow is moving into the page, then all of the velocity vectors would look something like that, but they're all sort of moving independently of one another, but they also interact by pressure forces and frictional forces and things like that that we're going to discuss. So I'm just going to maybe move over. This is so important, I'll go ahead and ignore it here. So let's suppose that this particular parcel, we'll say it has a center. So each parcel has a little center. You can think of that as just a geometrical center of the little cube. And I'm going to call that center x sub p of t. So this is the vector position. So if the origin of our coordinate system was down here, then the position of the particle would be the position vector, if this is x equals 0 down here, for example. And it's the sub p means it's the parcel position. And then the fact that it's a function of time is because this parcel's moving around. So its position is changing over time as it flows with the velocity field. Okay. So the key mathematical property of a fluid parcel is that it moves with the velocity field, moves with the flow, which is represented as if x sub p of t is the parcel position, we have that the rate of change of the parcel position is equal to the value of the velocity field at the location of that particular parcel. So this equation is really important to sort of make sure that it's clear, because it looks a little bit complicated, because you have sort of xp is on both sides. On the left-hand side, it's differentiated. This is sort of the velocity. This is the rate of change of the position, which is velocity. And all it's saying is that the velocity of the particle is equal to the velocity that's given by our velocity field at the point where the particle is. So as an example, so let's say, and so it's maybe a little bit conceptually confusing, because like, do we have this u, do we not know it? So here we're imagining that we know the velocity field. Somehow we have figured it out. And what this tells us is, let's say the velocity field looks like this. It's some kind of vortex that goes around. Then if we have a parcel, and that parcel is at this location, it says the velocity of the parcel is that it follows the velocity field around. So here the black dots are u of x, the black arrows are u of x, and then this vector is xp of t, and that would be the xp dt. So the parcel is basically embedded in the flow, and it moves with whatever that velocity field is. And so, okay. So, oh, and I'll say, so there's two extra notes here. So this equation, so this property of moving with the flow is called the Lagrangian property. So anything in fluids that moves with the flow, that just gets kind of passively blown along with our wind or whatever, anything that does that is called a Lagrangian. And so in this case, we call it a fluid parcel, but very often they're also called Lagrangian parcels. And it's not just these hypothetical sort of small imaginary blocks of fluid that can be Lagrangian. Also in practical oceanography, for example, let's say you have a surface float. So you have just, you want to make measurements, so you just put a float in the water, and then that float has instruments on it that send back data. If that float is sort of free floating, it'll basically follow the surface currents. And so those are called Lagrangian floats, and then it gives you a Lagrangian picture of what the velocities look like. The equation, I'll call this the star, is called the kinematic equation. And here, the word kinematics is distinguishing from the word dynamics. So usually when you take first year physics, they discuss kinematics and dynamics. And kinematics is just a description of how things are moving. So like, you know something's velocity, you know its acceleration, so this is how it's going to move. Whereas dynamics is what happens when you start to talk about forces. Basically, forces are the dynamics, and that determines the kinematics. But so this equation here has no forces in it. It just says if we know the velocity field, then we can tell how that's going to move parcels around. And so this is very, very important setup, because it's by looking at these Lagrangian parcels that we're going to be able to write down an equation that tells us how to predict the velocity field. Okay, so to derive a predictive equation, for the velocity field, we will use Newton's second law. And so we apply that to our particle. So we have some fluid parcel. It's got some position xp of t, and then there might be some forces acting on it. We're going to come back to what those forces are. But in general, we have some particle has some position. That Newton's second law is that the mass of the parcel times the acceleration of the parcel has to equal the force. And the acceleration is just the second time derivative of the position. So this equation will ultimately become the Navier-Stokes equation. But there is some work to do first. Okay. So here's the program. So we're going to think about Lagrangian parcels that are just passively being moved around in the velocity field. And we're going to try to rewrite Newton's second law, which is just mass times acceleration equals force. But we want to somehow write this in terms of the velocity field, because we want to get an equation that allows us to predict what the winds will be like in the future. So we want to know the velocity field in the future. And we see there's some link, because the speed, the velocity of these parcels is related to the velocity that we get from the velocity field. So this equation is linking particle dynamics, parcel dynamics. Some people say fluid parcels, some people say fluid particles. I'll definitely mix those up constantly, but it's the same thing. But so this equation, the kinematic equation, links parcel movement to the velocity field. And then this equation links parcel movement to forces. And so we're going to basically connect these two and link forces to the velocity field. And that'll end up being the Navier-Stokes equation. Okay. But first, we really need to do some work on the acceleration of the parcel. Because right now, it's unclear exactly how this is related to the velocity field u that we're looking for. Okay, so here's a new section. This is 3.2. Acceleration of a Lagrangian parcel. Okay. So we will now transform the parcel acceleration so that it is written in terms of the velocity field u. Okay. So our starting point is just the normal definition. The acceleration of the parcel is equal to the second time derivative of the parcel position. And we can split this second derivative into two first derivatives. So this is equal to d by dt of dxp dt. And but this dxp dt, we know from the kinematic equation, just by the definition of what a Lagrangian parcel is, it has to move with the flow. So this piece here, dxp dt, that equals, by the Lagrangian condition, u of xp of t And we always include this comma time here because in general, fluid flows, they vary across space, but they also change in time. And so both of those types of variations are very important in terms of understanding the dynamics of fluid flow and predicting it. So, so we have here, this is equal to d by dt of u of xp of t and t. So I'm just going to pause there for a second, just to give us a chance. Okay. So, so this equation says that our partial acceleration is equal to the time derivative of the velocity field, which is evaluated at the partial position and at that particular time. And so the key point of potential confusion here is that this is the rate of change of this. So this is the d by dt is the rate of change with respect to time. And then we have this u, and u depends on time in two separate ways. It depends explicitly on time, that's that comma time. So that just means that our velocity field might be speeding up or slowing down overall. But also, because we're looking at the position of the particle, if the particle is moving, then also the velocity can change because we're evaluating at the position of a moving particle. So there's like a little bit of confusion here. What exactly do we mean by this rate of change? How do we sort of sort this out? And it's helpful, in my opinion, to just go back here to the definition of the derivative and just write out this expression in terms of the definition of the derivative. So what do we mean by d by dt here? Since u of xp of t depends on time in multiple ways. So it's simplest to return to the definition of the derivative. And if you want to understand what some symbol means, just going back to the mathematical definition, usually a good way to start. Can't really go wrong doing that. So, we have the acceleration of the particle, which is a function of time, is equal to d by dt of u of the position of the particle and also its own intrinsic time dependence. And so this is equal to the limit, as delta t goes to 0, of u of x sub p of t plus delta t and t plus delta t minus u of xp of t and t divided by delta t. And so again, this looks complicated. There's going to be a bunch of formulas sort of in this derivation that look complex, but they will boil down to something quite simple in the end. But the key here is all we've done is, so the normal definition of the derivative is you take your function, evaluate it at t plus delta t, and in this case, our u depends on t in two ways, the particle position and the explicit time dependence, and so both of those get modified to t plus delta t. And you subtract off u just of t, and then divide by delta t, and that's your traditional definition of the derivative. But in this case, it's just a little bit more complicated than normal because the function has a more complex functional dependence on the time variable. Okay. So if we could evaluate this limit, then we would have our acceleration if we could do this limit. And it turns out Euler had this great insight of how to actually calculate this limit directly. And we're going to use Taylor's theorem to do this. So the key thing that we're going to do is we're going to do a little bit of simplifying work. So this first term is really where all the complications lie, because it's our velocity field evaluated at the particle position a little bit in the future, and at the time a little bit in the future. So we will simplify this part using Taylor's theorem. So just as a reminder, so Taylor's theorem in 3 space plus 1 time dimensions is that if we have any function, f, and we're evaluating that function at x plus delta x and t plus delta t, if you just go back in your notes, you should put x naught here and t naught here. That's given by f of x naught t naught plus delta x dot the gradient of f evaluated at x naught t naught plus delta t times the partial time derivative evaluated at x naught t naught. And so if we expanded this out, we would get 4 terms, actually 5 terms. We have our base term. This delta x dot grad, so this expands into delta x times d by dx, delta y times d by dy, plus delta z times d by dz. So we have 3 spatial derivative terms here, and then plus the time derivative term. And so we have 1 term coming from the explicit time dependence, that's that partial time derivative, and then 3 terms coming from the spatial dependence. So this is just the formula straight out of the notes from a couple classes ago. And now this is the first time we're going to apply this to fluid mechanics. We're going to apply this formula to this thing, because we have exactly something similar. We have u evaluated at some t plus delta t stuff, and so we can simplify using Taylor's theorem. But there's one step that we have to do first. So. Before we apply this theorem, we need one more simplifying step, which is we have in our velocity that we're trying to simplify, we have the velocity evaluated at the future particle position. And so we actually can simplify that first. First, let's simplify x sub p at t plus delta t. So that's the quantity that's inside our velocity field there. So this thing, we can use Taylor's theorem just in time to expand this. And so we can write that as xp of t plus delta t times dxp dt. And we used to write plus order delta t squared. And actually, I should have written over here, there is actually an error term here, plus order delta squared. I forgot to write that. Okay. So, our velocity here of our particle, because our particle is Lagrangian, dxp dt is just given by u. And so we can write x p of t plus delta t equals xp of t plus delta t times u of xp, t, and t plus order delta t squared. Okay. So again, this is an equation that looks a little bit complicated, again, because we have this xp all over the place on the left-hand side, the base point term, then inside the velocity here. But really, this equation is something very, very sensible. And what it says is, if we want to know what's the position of our particle at some point delta t in the future of where we're looking at right now, then that particle's position is going to be equal to its current position plus a small perturbation that goes in the direction of the velocity of the particle, right? So it's where it's going to be in the future is where it is now, plus a displacement due to its velocity. And you can recall, this has the same form. So recall from first year mechanics, we have that usual formula, x is equal to x naught plus v naught t plus 1/2 at squared. It's the classic kinematics formula. And this is really the same thing as this formula. We have our position in the future is equal to our baseline position, x naught, that's the same as this, plus v naught t. So here, the v naught notation, we're using u for that, but it's the same idea, that's the velocity times the time. And then if the amount of time that is elapsed is very small, so we're going to we're taking the limit here on the right, over there, we're taking the limit as delta t goes to 0. So if time is really, really small, then this quadratic term, we can just cross that out. So we basically just get x as x naught plus v naught t. And that's really all this is saying. It's saying if we want to track the movement of a parcel, we just need to know where it is now, what the velocity is, and that gives us the position a short time in the future. Okay. Okay. So we're trying to ultimately, what we're doing here is we're trying to simplify this limit, and we're trying to get an expression for a sub p for the particle acceleration. And we have to take this limit, but to take that limit, we need to simplify this velocity evaluated at the future position. And to do that, we first simplify what that future position is. That's the present position disturbed or displaced by the velocity local to that particle. Okay. So, using this, we can now simplify the complex looking quantity so the thing we're dealing with here is u evaluated at xp of t plus delta t and t plus delta t. So this thing here, that's just rewriting this person that's in the limit that we're working with. Okay. So the first thing we're going to do is this xp of t plus delta t, that's the future position of the particle, and we just expanded using Taylor's theorem what this looks like in terms of the baseline position plus this perturbation due to the velocity. Okay, so we can immediately rewrite this as u of xp of t plus delta t times u of xp of t plus order delta t squared, and then we still have our t plus delta t hanging out. So it sort of looks like we've made things worse because now we have 3 terms here instead of 1. But the nice thing now is that everything in here is evaluated at t. All of these particle positions are evaluated at t rather than t plus delta t. So now we can actually apply Taylor's theorem. So we now have essentially, if we look at the structure of this, we have our function u, and it's evaluated at the point xp at t and the time t, and both of those have a small perturbation. There's a small perturbation here, proportional to delta t, and there's a small perturbation to the time, also delta t. And so we can now use this Taylor's formula. So we can now directly apply. Taylor's theorem with the substitutions. According to this formula here, are the delta x that we're using. So delta x is just this stuff. So it's whatever is added on. So we have our x plus our delta x. So delta x is whatever is added to xpt. So that would be delta t times u of xp of t plus our error term. And delta t just equals delta t, because all we're doing here is we're adding on delta t as usual. So we're going to take our function and expand it, and we're going to have a base point term plus a delta x dot gradient term plus a partial time derivative term. Okay. I'll just pause actually. The sort of algebra and the notation can get a little bit complicated. And feel free, obviously, if something's not clear, the lectures are going to be posted, and also you can do this is all in the notes. And it often does take a few reads through of this particular derivation to have it really click. But does anyone have a question that they think can be clarified in the flow of things? Does anyone have a question? Yeah. If you review it later and you realize you're confused about something, we can bring it up next class, or we can talk. Or you can send me an email. And I think the notes should be very much consistent with what we're doing here in class. So we're just going to make this substitution. And so now what Taylor's theorem tells us is we have from the theorem, then from the theorem, we have u of xp of t plus delta t plus delta t equals. So now we write down our three terms. So the first term is the base point term. So just x naught, f depends on x naught and t naught. For us, x naught is just whatever is not the perturbation proportional to any deltas. So x naught here is xp of t. So we get here u of xp of t, and then just t. So we're not in this because our base point doesn't include this delta t. Then we get our delta x dot grad of, in this case, u. And then we get our delta t times partial u partial t, and then we get our error term. And now for our delta x, we can plug in what we wrote here, that our delta x is just delta t times the velocity plus an error term. So let's just write that out explicitly, one more step. Now for delta x, I'm going to write delta t times u of xp of t and t plus an error term and this whole thing is dotted with a gradient, and that comes from the theorem. So I understand this looks ghastly at first, but this is going to simplify very soon. So we just plugged in our delta x using our Taylor's theorem. So we have our perturbation due to this is the movement of our particle due to the perturbation from the velocity, plus our error term dotted into the gradient that operates on u. And then plus our delta t partial u partial t plus our error term. Okay. And so now we can simplify it a little bit just by organizing our terms. So we get u of xp of t plus, I'm just going to take delta t u dot grad. I'm going to drag all of the error terms and just sort of combine them into one. So we have here delta t times u dot grad of u plus delta t times partial u partial t plus some error term that's now gotten more complicated. We have some errors from here and some errors from here, but ultimately we're going to take the limit as delta t goes to 0. So all these errors are going to be ignorable in the limit that delta t goes to 0. But I'll just write down. So now there's a factoring that we can do. So again, we're expanding out. What does the velocity look like at the future particle position at the future time? And we're trying to do that because we want to get the acceleration. And what we find is that we get here u of the original particle position and the original time. So the new velocity is equal to the old velocity plus delta t times partial u partial t plus u dot grad u plus an error term that's proportional to delta t squared. So what we did here was we had a term here proportional to delta t that involves u dot the gradient, and that's coming from this spatial derivative term in Taylor's theorem. Then we had another term proportional to delta t that was proportional to the partial time derivative, and I just grouped those together. So we have our spatial derivative term, and we have our time derivative term. They're both proportional to delta t, and then we have whatever's left over from our various Taylor series of an error term of order delta t squared. Okay, so we're very close now to the formula for the acceleration. We just have basically just a couple more lines. I'm going to leave this board here because this is sort of the setup, and I'm going to erase that board so I can still reference sort of Taylor's formula and the definition of the acceleration. Okay, so the last step is what we've been doing is we've been working on. This is the velocity sort of one step in the future. So we have so the idea is that we have our parcel, and it has a particular location xp of t, and it has a particular velocity. And that velocity is u of xp of t at t. And then the idea is that at some point in the future, a short time later, it has moved. And now it's at some new position. And the new position is xp of t plus delta t. And the velocity has also changed a little bit. And its new velocity is u of xp of t plus delta t and time. And what we're tracking is how does the velocity of this parcel, how does that velocity change in the little time interval delta t as this parcel, which is the Lagrangian parcel, as that parcel follows the flow. So it follows the flow might be changing in time, it's also changing in space. And so how does this parcel accelerate? What's the derivative of its velocity? And so this sort of expanded expression here is the future velocity. This is our approximate expression for what the velocity looks like at this point, so this vector. And in our definition of the derivative, what we have to do is we have to compare that future velocity to the current velocity, take the difference and then divide by delta t, and that's our definition of derivative. That's our limit. Okay, so we can now plug this expanded expression into the definition of the derivative. And so what we get here is we have just rewriting the definition of the derivative. This equals the limit as delta t goes to 0. And this long expression here is what's in that, is we can plug it in for what's circled on the right-hand side there. So we get u of xp of t and t plus delta t times partial u partial t plus u dot grad u plus an error term proportional to the square of delta t. So that's just plugging this bottom expression in for that circled thing. And then we subtract off, in the definition of the derivative, we subtract off the previous, the current velocities. We subtract off u of xt, t and t. And then we divide that whole thing by delta t, and then we take the limit. Okay. So this seems like we made a lot of problems and didn't do much, but actually now it becomes very simple because something nice has happened, which is that this term here, just u at the particle position and the current time, and this term here is actually the same exact term. So this piece that we subtract off from the definition of the derivative actually cancels the base point term from our Taylor series. And so these two pieces actually cancel each other. And then furthermore, the delta t in the denominator here that comes from the definition of the derivative, this piece, and then that factor of delta t, they can also cancel each other. And then we're left with an error term that's order the square of delta t, divided by delta t, so that would be order delta t to the first power, and then in the limit that delta t goes to 0, this is really negligible, because this is a quadratic term, it's divided by a linear, so in the limit that delta t goes to 0, that whole thing, that error term still goes to 0. So this part here goes to 0. And so we can evaluate this limit, and we're just left with the acceleration of the particle as a function of time is equal to the explicit partial time derivative of the velocity field, plus this thing, u dot grad u. And these are all evaluated at the parcel position at that particular time. Okay. So that probably seemed a little bit on the gross side, but the formula in the end is so this is actually a very nice formula, because what it has allowed us to do is this is the parcel acceleration and so we've written the acceleration of this parcel, which is how its velocity vector changes as it moves. That's the definition of acceleration. And we've written that particle acceleration in terms of derivatives of the velocity field. And so this is exactly what we were trying to do. So what we're going to do now over, especially the next class, is we're going to really try to dig into what do these symbols mean. So how do we actually calculate, and interpret this formula, and we'll get lots and lots of practice. So if it looks a little bit arcane right now, you will get ample opportunity to practice with this formula. So this formula will be very important. And it's useful to expand it out for clarity. And so when we see this u dot grad, so remember, so u is the vector uvw, and these would all be the particle positions here. So u, so the velocity vector here is the vector uvw, and we dot that with the gradient vector, and the gradient vector is the vector of partial derivatives. And so when we write this sort of weird-looking construction u.grad, this is really a derivative operator. When we take this dot product, we take the product of the first two, the second two, and the third two, and we add the third pair, and then we add them together. And so we get here u times d by dx plus v times d by dy plus w times d by dz. Okay. And so our final formula in expanded out terms is that our parcel acceleration is equal to du dt plus u dot grad u, which equals du dt plus u d u dx plus v du dy plus w. Okay, so again, this probably looks a little bit mysterious for the first time seeing it. I know for sure it did for me. But so I'm gonna just so I'm just gonna stop it there. So we're out of time. But now next time we're gonna dig into actually doing some examples with this formula. So how do we use it to calculate given a particular flow, and how do we interpret the various terms? And we'll sort of think about like what does this mean for a particle going down a river and things like that, and we'll really interpret what this acceleration means, and also how this u.grad construction shows up in other cases as well. So again, don't worry if it seems a little bit complicated. You'll get used to the applications, and we're going to start those next class. Okay, great. So if you have any questions about the assignment, please just let me know. And other than that, I will see you guys in a couple days.
Thank you. Thank you.